Okay, guys, welcome to our lesson today on light and the electromagnetic spectrum. So, we got done talking about the nucleus of the atom and how isotopes are the same element that vary in the different numbers of neutrons, but that's basically it of the nucleus that we're going to be talking about until in May. Right now, we're going to talk about the most important part of the atom, and that is the electrons in the space that they actually occupy. There's a lot going on there. This was a lesson that was done in class, so it is a little bit more of a complicated lesson. The amount that you will be required to know of this kind of higher level information is not too much, but if you're interested in it, I will probably go in a little bit more detail with it today. But you will absolutely need your calculator at the end of the lesson. We will be doing some calculations on light, and I'm excited to talk about the electrons. All right, so this was the point in class where I would light some things on fire, which is always exciting. So the demonstration that I did is I put a bunch of different chemicals on the table and then I light them on fire and they burned different colors, which is super interesting. So here we have different elements giving off different colors of light. Well, what is going on with all of these colors? And how does the color change depending on what the element is? So let's go back to Bohr's model of the atom, which once again was the last model of the atom that we started to look at with our first lesson on the development of the atomic theory. So Bohr was the guy who proposed that electrons are found in these specific circular paths or energy levels orbiting around the nucleus. He thought that, okay, the closer to the nucleus you are, the lower the energy level, the lower the energy of the electron, and the further away from the nucleus you are, the higher the energy. Okay? However, Bohr's model couldn't really explain some of these physical or chemical properties of different elements. Like I just showed you, all of these weird different chemicals that I put on my table and lit them on fire, they burn different colors. Like, what is going on with that? So do the electrons have anything to do with not only their ability to burn different colors, or their ability to just kind of react with other things? So this is the point in the lesson where I got out my gas tubes. If you'll remember, J.J. Thomson's experiment was with a cathode ray tube, very similar to the gas tubes that we showed in class. Basically, I put in an electrical source that made the gas particles glow. Once again, Thomson saw that those glowing gas particles were able to deflect towards a positive end, and in that discovery, he learned that there was a negative particle called the electron. So what we're looking at here, though, is different elements that I had here of gases are burning different colors. Now, this is a perfect representation of what light is. You guys, it is all about electrons. Every single light that we see here on Earth, even stuff that we do not recognize as light, stuff that we just see is radiation reflecting off of that thing and into our eyeballs. So, and it is all due to the electrons in all of the atoms that make up the matter around us. So light is a form of electromagnetic radiation that travels like a wave through space as photons. So photon is an energy unit of light. Now, if I'm looking here, I've got different colors of the rainbows, right? And hopefully you guys are familiar with the light from the sun actually representing all of these colors of the rainbow. When all of the colors of the rainbow come together, they do in fact make white light. But one thing I'm noticing here is each one of these light wavelengths is a little bit different. Like if I'm purple right here, it's like it's happening a little bit more frequently. We'll learn about the term frequency here in a second. But then if I go down here to red, that wave looks like it's a little bit slower. So depending on the color, it looks like these wavelengths are a little bit different. Okay, so how does this come from electrons? Okay, I'm gonna switch to my document camera real quick. I want us to add something to our cute little picture. So you guys kind of have what I have up here. I made my picture a little bit darker so on printing it would look a little bit better. But basically what happens is when electrons get excited by some energy source, whether it is electricity like my gas tubes, or it is heat like fire, or if it is even another particle of light coming in, they get excited and they will actually jump from whatever energy level they are originally in to a higher one. It's like they get excited. I don't know about you guys, but when I get excited, I like want to jump up and down. That is what these electrons are doing. Now, eventually you need to come down from that excited state, and so the electrons will eventually fall back down. So we got electrons jumping through energy levels. To jump up, it looks like they need an energy input of a photon or energy source coming in, but when they fall down, they give off energy. And this energy is in the form of light. So on our cute little picture right here, what we're going to show is we're going to add those energy sources coming in. So we're going to say that this is energy. And a lot of times that can be light, like a photon. Sometimes it can be heat. Sometimes it can be electricity. Yeah. And that'll get that electron to the excited state, but it eventually always must come back down, and it spits out a photon of light. And depending how high that electron jumps and falls back down, we actually give off different colors, which is super exciting. Okay. Now, the key thing here is because since Bohr said, okay, we're in certain perfect little energy levels, electrons must be found in these energy levels. I can't have an electron just free floating in between energy levels. He's got to jump up and hit an energy level and then fall down and hit an energy level. So I can't just have any possible amount of energy input able to get the electrons to jump through the atom. It's got to be a certain specific wavelength that will get an electron to one energy level from another. Okay, the term for that, little chunks of only specific required energies, is called quantization. So this light energy is quantized. So only certain energies are required and therefore allowed to move electrons from one energy level to another. And we'll see what the result of that here is in a second. But the main thing I want you guys to take away from this part is that here is kind of a little, I had my little Bohr model here of showing the energy levels as circles around the nucleus. This is showing my energy levels in terms of the lowest energy level, or energy level number 1, energy level number 2, 3, 4, 5. It's showing the energy levels in order of increasing energy. If you'll notice here on my y-axis, it is showing that this is an increase in energy. So a lot of times when we write energy levels, we will specify the first energy level as n equals 1. That would be n equals 2, et cetera, et cetera. So the interesting thing here is that the distance between the energy levels is actually not all the same. The jump to go from energy level 1 to 2 is like wildly crazy higher than the other ones subsequently. And we'll look at more accurate pictures of what this looks like here in a second. But it is not as simple as these all being evenly spaced together like the Bohr model shows. Anyway, the key thing here is what we've kind of been talking about so far is that here I have energy coming in to have that electron jump from a ground state to some sort of excited state. That process is called absorption. Okay, and up here on this picture right here, it says the word absorption. So we're going to summarize right here. It says energy is absorbed as the electron jumps up to an excited state. Yeah? And then once he gets done being at his excited state, he then falls back down. And the result of that is that he releases energy. The term for releasing is an emission of energy. So it says a photon of light is emitted as the electron falls down back to where he started from. We call where he started from his ground state. So that's super exciting. That's actually what's happening inside of the atom that is causing all light. Okay, so like I mentioned, when the electrons fall back down to ground state, depending on how far they fall, they will give off energy in the form of different colors of light. So remember our original picture that we saw here of all these different wavelengths of light, and we were like, hey, that red one looks a little bit longer and stretched out than the purple one. Well, that is very true. If you'll notice this short little jump up and down from energy level 1 to 2 and back down to 1 again creates maybe a lower, sluggish, more energy light color. But if I'm jumping all the way up here to 2 or 5 to fall back, that is a long jump. I bet that's going to require a lot of energy to get up there. And then on the other hand, it's going to require a lot of energy, an amount of a lot of energy to fall back down. So one thing I want you guys to know on this picture, it's showing different length jumps. The different amount of energies that are going to be required for those falls is going to create a specific energy of light, which will be represented in a different size wave and therefore different color. Okay, now this is super important because I could have all sorts of things happening in the atom. So to kind of go back to my last picture, all of these jumps could be happening simultaneously, and the net result of that is my eyeballs see maybe some purpley blue thing, okay? I do not see a blue and a light blue and a red, okay? But what I can do is I can put all of that light shining through that atom, all of the various jumps, through a prism, okay? And in that prism will break up that light, all of the different jumps that came together to make whatever that initial color that I see with my eyeballs is. It'll actually break up what those colors are for me. And then I can see specific quantized energies of different light that, you guys, those represent the different jumps that were allowed for the electrons to make in that atom. If you will notice, I do not see a full color of the rainbow here. No. That's because this light energy is quantized. Those electrons just cannot go woo all over. They have to hit specific energy levels, which means you are going to see bands of light that look like this. Now, we know atoms of different elements look a little bit different. That includes the number of electrons they have and what energy levels those electrons are found in their ground state. So as a result, you guys, every element has a unique, what's called an emission spectrum. And these are the colors that you see that represent that specific element's electrons jumping up and down through the energy levels. So this is crazy, you guys. Look at the hydrogen one right here. We know hydrogen is atomic number 1. That means he has 1 proton, and he also has 1 electron if he is a neutral atom of hydrogen. And these are the specific bands that just that 1 electron can make jumping through the energy levels. Now, we showed in our picture that we're going to probably go back to here in a second. Yes, here it is. That if I don't jump very high, I create a very low energy color. Well, hey, y'all, this guy right here, that is probably a low energy level jump for hydrogen, right? And then the higher I jump, I create higher energy colors. So looking down here, oh my gosh, these purpley things are probably some of the highest jumps that an electron can make. And now here's a spectrum for sodium. We got one for helium, we got neon, we got mercury, and we've got different numbers of electrons in all of these atoms. And you guys, this is exactly how we have been able to figure out what the planets in the solar system are made up of. We have looked through a telescope, we have taken that light energy coming from that planet, we have broken it up, and we have determined what elements have created that specific emission spectrum that I see from the light energy from the planet giving off. Isn't that amazing? We are able to indirectly discover things without physically being on Jupiter or something. That is amazing. Okay, so I actually want to, if you have some colors, I do find this may be kind of helpful, because we can actually add some of these colors. I'm going to grab a little red thing, and I'm going to show that, hey, this lower energy jump would represent a lower energy wave color, which do not get worried. You were like, how does she know red is low and purple is high? We're about to map that out here in a second, okay? But that one is going to be a red one, the kind of middle-sized one. It looks like I had kind of a light greeny blue, right? And then this super energetic wave was my like dark blue, probably purple thing. And it is so energetic that it is even hard to see all the very, very, very cool. So once again, the summary here, guys, is that these long jumps are represented by high energy colors. And teensy tiny short jumps are represented by low energy colors, right? Okay, now we're going to switch to the document camera. We're going to talk about the electromagnetic spectrum because, y'all, these colors of the rainbow are not the only type of light that electrons can give off flipping through the atom. We got a whole giant spectrum here, and only the visible light part is such a small part of it. I've got stuff like ultraviolet, X-rays, gamma rays, right? I've got stuff like infrared, microwaves, radio waves. So we're going to kind of expand on all of this because there's a lot going on that we maybe cannot even see in terms of the visible light spectrum. Okay, so let's see. We're going to map out our electromagnetic spectrum, and this is so super fun. I'm very excited. The first thing you're going to do, and I feel like every year, like I struggle to create a nice gradient of a wave going from low energy to high energy. So you may want to watch me first before you start trying to tackle this guy out. So on the electromagnetic spectrum, it starts with waves that are kind of like real slow and sluggish, and then it gets a little bit more crazy. Yeah, so that is not perfect by any means. In fact, this is like real sloppy at the end, and my perfectionist self is like, oh God, I can't even look at that. Yes. So basically what we're looking at here, you guys, is that the full electromagnetic spectrum is a gradient going from really slow-ish waves, and we'll get to some terminology like energy and frequency and stuff here in a second, until we're like got this wave that is like crazy energetic here. Okay? Now, only one middle part of this spectrum is called the visible light spectrum. So I'm going to write visible. Okay, this is the light we can see with our eyeballs, okay? Everything else is invisible to us, which when we talk about what the everything else is, you'll be like, I did not know that was light. And it is. We just cannot detect it with our eyeballs. Anyway, so our visible spectrum is going to be the colors of the rainbow. We have Roy. We have G, Biv is the way we remember the colors of the rainbow. Red, orange, yellow, green, blue, indigo, violet, okay? Now, depending on the size of that wave, we can kind of measure them in terms of their wavelengths. We will talk about what a wavelength is later, but for right now, let's just go ahead and say that a red wavelength of light is roughly around 700 nanometers. And a violet wavelength of light is roughly around 400 nanometers. So this is kind of the section of the spectrum that we can see. Everything outside of this visible spectrum we cannot see. So what happens when I jump out of violet and go this way? You guys, we got ultraviolet. So ultraviolet. And you were like, ultraviolet, UV, is that like the rays from the sun? Yeah, it is. It's the stuff that gives us a sunburn, but it is light. It's not light that we can see. The sun gives us a ton of light that we can see. All of those will fall under my visible spectrum, even though it looks like white, okay? Now, outside of ultraviolet, the next more energetic wave is X-rays. Like you go to the doctor, they give you an X-ray. Y'all, that's light. It's a little bit more spooky and scary because of more energy, and I definitely cannot see it. And then our highest energy waves are called gamma rays. And you're like, oh, that sounds scary. Well, it is. It is a form of electromagnetic radiation that could be damaging to human tissues, which is why we do not want exposure from that radioactivity. As you can see, that wave already looks pretty intense. There is no surprise that a gamma ray probably occupies a wave that looks like this. Okay, so back to our visible spectrum. Let's go this way to the more sleepy electromagnetic stuff. So outside of my red part of the visible spectrum, you guys, I got infrared light, right? And that is the light that we cannot see, but a lot of times if they have like a, I'm losing my brain, like a heat sensing camera, a thermal sensing camera, those are the waves that thermo sensing camera can pick up to where you can see different temperatures of something, okay? We cannot see that without that technology with our own eyes, which is why it is outside of the visible spectrum. Okay, outside of infrared, moving this direction, we got micro waves. And yes, I mean like microwaves, like in your microwave. That is light. You were like, there is no way. Yes, it is light, which is so wild and crazy. And then finally down here on my slowest stuff, we have radio waves. And like the AM frequencies are a little bit lower energy than my FM frequencies. I like to think about y'all probably don't even listen to radio station anymore, but there are two radio wavelengths, the FM frequencies and the AM frequencies. I like to think the AM frequencies are the channels that only the really old people listen to. It's like the news or like oldies music. So they're the more lower energy. The FM radio stations play like more of like the top 40, stuff that we would like to listen to. No matter. So you guys are going to be responsible for knowing for the order of all these things in the electromagnetic spectrum. And y'all are like, Sabaka, you're making us memorize again. And I'm like, no, I got a thing to remember all of these orders. I like to say red Martians invade Venus using X-ray guns. So we're going to write that up here because that is helpful for us. Red Martians invade Venus using X-ray guns. Yeah? All right. So once again, R is for radio, M is for micro, I is for infrared, V is for visible, U is for ultraviolet, and X-ray is for X-ray, and then guns is for gamma rays, which is super cool, super fun. Okay, so this is our electromagnetic spectrum. Okay, so I'm going to bounce back, I think, to... No, I'm not going to bounce back. We're going to flip to the back of our notes page, and we're going to talk about light and all of these properties of light. Okay. So it says movement of the excited electrons to jump from lower energy levels and the subsequent release of energy is seen as light. Before 1900, scientists thought that light behaved as a wave. You were like, what do you mean thought? You just had me write out an entire spectrum where I had waves. And I'm like, yes, okay, we're getting there. And it says this belief changed when it was later discovered that light also had particle-like characteristics. And y'all are like, what is happening, Sabag? I don't even know. We're going to get there. But this is called, this idea that light can act like a wave or act like a particle traveling through space is called the wave particle duality of light. A duality means that you have properties of two different things at the same time. Y'all are like, okay, let's first look at light as a wave. And when I'm talking about light as a wave, I am thinking literally in my brain, like, ooh, traveling like a wave through space, which there is no surprise here that we have a wave here. Let's start kind of clearing up some of these terms like wavelength and frequency and all that fun stuff. So the first thing I want us to look at is that the waves go up and down like mountains and valleys. Right? We have terms for these mountains and valleys. The tippity top of a wave is called a crest. The crest of a wave. And the bottomy bottom of a wave is called a trough. Okay? And the crests and trough kind of cycle up and down through this kind of main general area here, which we call the origin. To where if I were to squish the crests and the troughs together to kind of create that average of where that wave pattern is traveling through, that's what the origin is. Okay, now different waves can jump up real high and fall down real low, and some waves can go up a little bit and down. So we have a measurement for that. So the height of a wave from its origin here to the tippity top of its crest is what's called the amplitude. Amplitude spelling, yes. Okay. Now, the most important feature of a wave that we will be utilizing from this diagram, that is one that I want you guys to most importantly recognize, is what is called wavelength. A wavelength is the length of a wave. You're like, okay, that makes sense. But what part? Is the length of a wave from the crest of one wave to the crest of another. This represents one wave cycle. To where if I were to, oh my gosh, you guys, there's a fly on my page. Okay, woo, whatever, okay. So if I were to look that wavelength and I would to move over here, I would have another wavelength. So it gives you chunks of each wave cycle. The length of a wave cycle is called a wavelength. And y'all are not ready for this symbol. This is a Greek symbol. it looks like an upside down Y. It is called a lambda, okay? So that is what we use to represent wavelength. Okay, so now it says the significant feature of wave motion and its repetitive nature, which can be characterized by the measurable properties of wavelength and frequency. Okay. So let's talk about these terms, wavelength and frequency. We talked about wavelength over here. It's something you can more visually see. Frequency is a little bit more abstract, but the two kind of go hand in hand to where they make sense together. So the wavelength, once again, the symbol is this cute little lambda, and that is the length of one complete wave. Since it is a length, we measure a wavelength in units of length. And in the metric system, units of length are meters, nanometers, centimeters. Since usually we're dealing with the electromagnetic spectrum, y'all, I already wrote nanometers here. We're dealing with very, 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 very small wavelengths. So most commonly, we're going to see nanometers. Honors kids, y'all going to be using nanometers a lot, okay? On-level kids, you guys are mostly going to be using meters, okay? But as you can expect, since I'm dealing with very small numbers, this stuff is going to require maybe some scientific notation to represent these little interesting wavelengths. Okay, anyway, so that's wavelength. Next one we have is frequency. And y'all are like, the symbol is a V. That is a Greek symbol that I've forgotten what the name is, but that weird, awkward V that looks a little bit fancy with a little tail on its end is the symbol for frequency in chemistry. Now, the frequency is the number of waves. And once again, when I say a wave, I mean a wave cycle that's represented by a wavelength. So it's the number of these that pass through a given point in a period of time. So I'm measuring how many or how long it takes for one of those to go through. Okay. Now, the tricky thing here is that the units for frequency are this weird thing called a hertz, H-Z. And in fact, y'all's radio waves, the 101.2 or whatever station stuff, those are measured in megahertz. So those are units of frequency. Now, I want to kind of break down what a hertz is really, because a hertz is kind of like a conglomeration of what the sciencey technical term for this unit is. The sciencey technical term for what a hertz actually is 1 over a second. And you were like, 1 is not a letter of the alphabet like a meters or a liters or stuff like that. And I agree with you. But that is because this one kind of represents a cycle, or 1 per second, like how many waves are going to pass through a per second. Okay, so it's like your units are just a per second, which is kind of weird and uncomfy. And if you were already confused, no matter, it'll be just fine. We were dealing with hertz here, but I wanted to explain that out because when we get ready to do some calculations down here, you're going to be like, where's the seconds? Why do I not have a second if I'm trying to cancel out units? And that is just because hertz is truly that. Okay, so it says all kinds of electromagnetic radiation create the electromagnetic spectrum, which we drew out on the other page, and they can be described by, yes, wavelength, yes, frequency, and I'm giving you another term, energy. And the symbol for energy is not a freaky one. It is a capital E. So we are dealing with wavelength, we are dealing with frequency, and we are dealing with energy. So what I want you guys to do now is I want y'all to flip back to your electromagnetic spectrum. And now that we know these terms, energy, frequency, and wavelength, we can kind of map out my different sections of the electromagnetic spectrum and describe what it means to have a low energy or a high energy, a long wavelength or a short wavelength, a high frequency or a low frequency, and how those terms, energy, frequency, and wavelength, actually relate to each other in terms of a direct relationship or an indirect or inverse. You were talking a lot, Sabaka, and I agree. Okay, so looking over here on this side of my spectrum where I've got real slow waves, if you were to ask yourself, are these high energy waves or low energy waves over here? Hopefully it is no surprise to you that these are low. So over here, if I'm over here on this side of the spectrum, I'm dealing with low energy. And the way I like to represent a value that is a low or a small value, if I have a low energy, I like to use arrows. If you see an arrow down in my class, that means there's low energy, okay? A smaller value. Now over here, it is like, okay, yeah, those definitely looked crazy more energetic. We would call over here high energy. And with my arrow notation, a big number would be used to represent a high energy wave, right? Okay, Now let's talk in terms of frequency. Frequency was something that we did not map out on our cute little picture on the backside, but the definition of frequency is how many waves cycle happen per second. So if I just kind of visualize that, whoa, I bet you this side over here looks like it's got a lot of waves happening very quickly in a short amount of time. And you would be right. So we would call this section high frequency. So I have high, and once again, the symbol for frequency is the weird V. You'll see it just look like a normal V just because I am lazy, but it is not V, it is, frequency. So we would say that this section has a high V. Energy and frequency are both up. That means if one is high, the other one is high. This is a direct relationship between these two values, and we're going to unpack that a whole lot more later. But on the other hand here, we've got, not a lot of waves passing through very quickly, right? So we've got low frequency over here. So arrow down frequency. All right, our last term, we got energy, frequency, and we got wavelength, okay? Wavelength is the length that you can actually see. So this is a little bit easier for us to visualize. It's like, y'all, over here, I got a big old space here from a two crest. This is a long wavelength. So long wavelength. Once again, I got my upside down Y. And to represent a long value would probably be a big number to represent a length of a wave. So I'm going to have an arrow up for my wavelength. And then over here, it's like, oh my gosh, the distance from crest to crest, the length of that is very short. So we're going to say that these are short wavelengths. So I would have smaller numbers to express a shorter wavelength. So I would have an arrow down for a short wavelength, okay? This is so important, and that is why we mapped it out on here, okay, you guys? So going back to our visible spectrum, I can even just within the visible spectrum kind of describe how a red wave would look compared to a violet wave. Well, violet's closer to this direction where I've got my high energy, very fast, frequent occurring waves. So it's no sense that my more violet waves, when we were talking about jumping up and down through the atom, represented really long falls, right? And then over here on my red section of the electromagnetic spectrum, I got more lower energy waves with the longer wavelengths. And if I got a lower energy wave color, that's going to be represented by a much shorter fall. Yes? Okay. So now if I flip back to the next page, right, and start where we came right off, it says the lowest energy waves on the entire electromagnetic spectrum are my radio waves, right? The ones that are over here. So radio waves. And my radio waves, you're going to see me writing these arrows a lot because you know it's important when Miss Zapaka does something over and over again. I'm trying to drive it into our brains because its importance is very, very strong. So my radio waves are low energy, and as a result, low frequency. And as a result, they're going to have a long wavelength. And then my highest energy waves with my shortest wavelength and highest frequency are going to be gamma rays. And they are going to be high energy. Whoops, that was a terrible arrow. And high frequency and short wavelength. So now you're noticing some of these arrows are going up and down together at the same time, and some are doing the opposites. This is where we get into the relationship between all of these properties. I want you to notice frequency, which is V, and wavelength. Those two things always have opposite arrows. So we would say frequency and wavelength are inversely proportional, which means if one goes up, the other one goes down, right? If I have a high frequency wave, it's going to have a short wavelength. Also, if I have a low frequency wave, it's going to have a long wavelength, right? Okay, but now let's look at energy and frequency. Energy and frequency, they both go down together or up together. We call that a direct relationship. So energy and frequency are directly related. And yes, you will be responsible for knowing how these properties of waves are related in terms of these terms. Okay, now let's see. It says, I think I want to switch back to my PowerPoint lecture. So let's get that doing right now. We went through probably a lot of this. Oh, there we go. So yeah, light is a wave. Cool. Okay, so in here you can kind of see it a little bit better. You know, I like my pictures because I like my visuals. So this is a low energy, long wavelength, low frequency wave. And then down here is the high energy, high frequency, short wavelength wave. Okay, now let's look at the particle nature of light. This is the one that is going to seem the freakiest to you, and it is also the one that I'm not going to require you to understand a lot about. I just want you guys to know that light does have this wave particle duality, okay? So let's kind of identify what that actually means. And on my page, I like to kind of remind myself where it says the light particles. Like up here for my light as a wave description, I drew a little wave. And now down here for light as a particle, I like to write the little dots traveling through space. Because you can just see the word particle and you're like, I do not know what that means. And now you're like, oh yes, that means a thing that is going like that. Okay, cool. So what we're looking at here, how we figured out that maybe light behaved as a particle too. It says in the early 1900s, scientists conducted experiments involving interactions of light and matter that could not be explained by the wave theory of light. One experiment involved a phenomenon known as the photoelectric effect. And this discovery of the photoelectric effect led to the description of light as having both wave and particle properties. Y'all are like, what is happening right here? So basically what the photoelectric effect did is they shined electromagnetic radiation, light energy, down onto a sample of a metal. Now what they would have expected to see is light energy as waves coming right off, right? What they saw instead is only distinct quantized colors of photons popping off, not all possible light energy like they had coming in initially. So this kind of also supports Bohr's model of being like, yeah, stuff is quantized. We get those perfect specific bands on the electromagnetic spectrum, right? Well, we now looked at light not so much as a wave, but as distinct quantized energies are known as particles. Okay, and there's an awesome video that I do not want to waste our video time here today, but I totally encourage you guys to look at it. You are not responsible for understanding the photoelectric effect, but if y'all are like, how is light a particle? What does that mean? That would maybe kind of clarify some of your questions. Anyways, it says a quantum of light energy is called a photon. Very exciting. All right, now we're going to switch directly to the document camera because as we're about to do some math time. Okay. We have two equations here that show how these properties of, frequency, wavelength, and energy are all related. So the first equation here is C is equal to, we know that is wavelength and that is frequency. According to my little directions down here, C is equal to the speed of light, 3.00 times 10 to the 8th meters per second. Y'all, all light, I do not care what type of light you are on here, they all travel at the exact same speed. But you're like, but they look so different. Yes, they do. They vary in what their energy and wavelengths are, but the speed at which all light travels is the same, and that is a constant known as this 3.00 times 10 to the 8th. So that just means every time you got to plug in something for C, it's going to be 3.00 times 10 to the 8th. Okay? Now, I also reminded you what the units are for your wavelength and what the units are for frequency. And I thought what I kind of like to do when we get mathy, I'm going to zoom in because that's a lot better. Okay, cool. When we get mathy, I like to really, really hammer home what units are going into these values when you put a number in, okay? So speed of light, that unit is down there. A speed of light, well, first of all, it's always going to be 3.00. So we'll just do that. 3.00 times 10 to the 8th. But the main thing I want to keep in mind here is his units are meters per second. So I mean a meters over a second. Well, I'm getting C is equal to the product of two things multiplied together. So let's see, wavelength, meters. So wavelength is meters. That's probably how the meters got on top. And frequency is hertz. But if you'll remember, when I was up here being like, y'all, hertz is actually a per second. This is where that makes some sense. So a hertz is a 1 over a second. So if I multiply something that is a meters times something that is a second on the bottom, that's where you get the meters per second, okay? Now, let's move over to this one. This shows, well, first of all, this one shows the relationship of wavelength and frequency being inverse. If one value is small, the other one's got to be big because the product has to always equal this. If one value is big, the other one's going to have to be small enough to where the product equals whatever that speed of light C constant value is. All right, now this equation right here shows the relationship between energy and frequency of a photon of light. So E is energy, and his units are capital J. That stands for joules. H is a constant. So we had a constant over here in our first equation, speed of light. It's always equal to 3 times 10 to the 8th. Well, Planck's constant is always equal to 6.626 times 10 to the negative 34th. His units are joules per second. And then V we know as our frequency. So let's kind of map out the units of this equation like we had on the other one. Okay, so energy, we said our units are joules. So that is a capital J. Now, joules is going to be given from something else coming into it, right? That means the product of whatever these two units have to spit out joules at the end. Well, H we said is our constant. That's Planck's constant, 6.626 times 10 to the negative 34th. And his units are joules times seconds. They stick it together, JS, but that's basically joules and seconds together. And then our frequency. Once again, our frequency is a little bit wonky. Hertz. But what is hertz really? 1 over second. So if I multiply a joules in seconds times or divided by a second, the seconds cancel each other out, and that's where you get to the joules, okay? So I'm giving you all this unit stuff because it is actually helpful and important. Also, it is super helpful and important because when you get down here to problems, you're going to see these things like hertz and joules and joule, and you need to know what letter of the alphabet or Greek alphabet that is representing so you can pick which equation you want to use. Now, on level kids, to help kind of enforce our math skills, because there are going to be situations where they're going to ask you to solve for wavelength. You're going to need to isolate wavelength on its own, okay? And we're going to be practicing that algebraic skill together. But the triangle situation, like our density triangle, can also be somewhat helpful, okay? So we could expand this out to be a triangle of our light calculations. We could put C up on the top, and we could put wavelength and frequency on the bottom. So you cover up with your finger what you're trying to solve for. If I wanted to solve for C, the fact that these two things are right next to each other means you multiply them. What if I wanted to solve for wavelength? Yes, I can move my equation around, and that is what I absolutely want you guys to start doing. But you can always go back to your triangle and check if the result of moving your equation around to isolate the variable that you're wanting to solve for is correct. So if I wanted to solve for wavelength, I'd cover up wavelength. Oh, wavelength would just be speed of light divided by that frequency. If I wanted to solve for frequency, speed of light divided by wavelength. If you rearrange your equation, you will get that exact same thing. Similarly, I can create a triangle for this guy over here where energy is on top. And then Planck's constant and frequency are on the bottom. And so the way I remember which thing goes on top, it is the thing that is by himself on one side of the equation. Cool? Okay, let's do some examples. So these are not super complicated math equations, but we're going to get tricked up because some of these will require us to use our calculator for scientific notation, you guys. Okay, so let's see. It says, if the frequency of a wave is 500 hertz, what is its wavelength? Guys, I am not going to depend on words to help me figure out what these numbers they have given me are. I'm going to circle what that number is and its units. And I'm going to look at that unit and be like, what hertz? That's a unit for wavelength, energy, frequency. And you're going to label it right then and there with a V. So you're like, whatever equation I use has got to have a V in it. Okay? The next thing I've got to search for is what they are asking me to solve for. I always like to box this off so that way you do not get confused. They're telling you to solve for a wavelength. Do not think they are asking you to solve for energy. No, no, no. We are not using this. We need to solve for wavelength. So wavelength, the symbol for wavelength is that. And I write my symbol and you're like, that is so lame and dumb. But no, I visually see a part of my equation that I need to grab and use. And, oh, so I got to use that guy, right? The thing that I'm solving for, the thing that I'm boxed off, I either cover up with my triangle, right? Or I rearrange my equation to show me how to solve for that wavelength. So if I'm wanting to, and I'll show you guys mathematically first what we were actually doing. To get wavelength by itself, well, I got to get rid of it over here, right? I've got to divide both sides by frequency, because then the frequencies go away over here and wavelength is by himself, right? And if I cover up wavelength on my triangle, that is what you see, C over V. So my equation, once again, I want you guys to show, let's see, I solved for wavelength, oh my goodness. Wavelength is equal to C over V. So you can either write that as your check for showing me your equation, or you can write that and then show your substitution with things figured out. I always kind of like to establish my equation in the way that I'm going to be using it to solve, but that is super up to you. I just do not want you guys to get confused, and I find that this helps me not get quite as confused with moving things around to isolate your variable. And honors kids, if you were like, she's like explaining this too slow, I am sorry, but we've got some on-level kids who are needing a little bit more math help, and you guys need some math help too. I'm not a great math student, so this is helpful for me too. Okay, so now we are ready to plug some things in. Apparently I got to plug in a C and I got to divide it by a V. Well, I got a V. What is the C? Speed of light. Always that number. So we're going to go over here and we're going to be like, yay, I love this. We got 3.00 times 10 to the 8th. And yes, you must put the units, because these are wonky units coming out of these equation calculations, and you will be confused if you do not know what you're supposed to get out of this, okay? And then my frequency is what we circled here. It is 500 hertz. Yes? All right, we are super ready to go now. I grabbed my calculator, and I got my old calculator, so do not laugh at me. We got scientific notation numbers, so do not forget that that E button exists for you, right? So I got 3.00. You do not have to write the 0.00 because that is a 3 times 10 to the 8th, but I'm writing it this way this first time just so you guys do not freak out and be like, why does my thing that I'm writing look different than yours? And then I hit that E button. Remember, that E button takes the place of all of this business, right? And then I just have to hit my exponent, 8. I don't need parentheses. I'm ready to divide by whatever it is. It is a 500 that I'm dividing by. Cool. So, I can't even see that. So we got that. Oh, we got a 6 followed by, it looks like 5 zeros. Yes. So that's my wavelength. You can't see. Here we go. That's my wavelength. Sometimes when I'm getting started, especially on these energy and light calculations, I kind of like to write down what my calculator gives me because I'm already freaked out here. This is crazy. Okay. So this is a wavelength. Wavelength. What are the units for wavelength? Well, we know that hertz is really over a second. So what I have here is I'm going to get meters out of it because the seconds will cancel off, okay? Or if you're like, I do not know how that makes sense, you guys, coming out of this equation, your wavelength always will be in meters. Always, 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 okay? So we got meters. Now we got to check sig figs. I am never going to look at my two constants, meaning speed of light is a constant. It is always that. I am sure it is 3.00000. I could write a billion zeros. You just do not want to write that on your page, and nobody wants to see that. So this will always be a lot more sig figs than anything else going into the equation, okay? Same thing with Planck's constant, infinitely significant. That means the only thing I have to look for sig figs here is the thing that they popped in. It's a tricky one. I got trailing zeros, but there's no decimal in that number. So you guys, I have one sig fig for this guy, okay? Well, that's not too bad. I have one sig fig in my answer. So you guys, this is an appropriate answer for me. I love that. Okay, moving on. So you see how the circling and identifying and the boxing off what you're trying to get to helps you pick and choose what equation you need to use. Is very helpful. Okay, we are moving on. So we go now. It says, what is the energy of a wave if the frequency is 300 hertz? I zone in on the number 300 hertz. Hertz is my unit for frequency, so I got another V. What are they asking me to solve for? Energy. Energy is E. Which equation am I going to use? This one. And I'm going to use this to solve for energy. Good thing for me, energy is already by itself. I can say energy equals this, right? So I don't have to do any triangle, any things, moving things around, which is great news for me. Okay, so I'm going to say energy is equal to H times V. Once again, I have my equation, right? The next thing I'm going to want to see is my substitution with units. Planck's constant is our constant. It will always be 6.626 times 10 to the negative 34th. His units are joules seconds, JS. And then frequency is the thing that they gave me, 300. Oh, I did not put a decimal in there by mistake. So let's go ahead and put that decimal in my problem so I do not forget that may be important in terms of rounding. Okay, so I got my calculator. I'm ready to go. Once again, E button tackles all of this stuff, right? So I got 6.626 E, right? Negative 34. Then we are going to multiply by, what did I have? 300. Okay, my calculator gives me this. I'm like, that is amazing. It is 1.98. It is also 1.98 whatever times 10 to the negative 34. So do not forget that your calculator is going to show you a little bit more information when you got a big number going in. Okay, now for sig figs, Planck's constant, I'm not looking at him. I'm looking at the number they gave me in the problem. That's got 3 sig figs. That decimal in that number is a very different situation than what I had here in the first problem. It makes those trailing zeros significant. So looking at my answer, I need the 1, I need the 9, I need the 8, and that's it. But I'm rounding that 8 up because 7 behind it tells me I need to do that. So I have 1.99 and then times 10 to the negative 31st. And the units for this is energy. Energy is always joules. Or if I'm like, I have forgotten what the units are for energy, that's where your units in here help you. Hertz is always a per second. So if I multiply joules in seconds over a per second, seconds go away, I got joules at the end. Amazing. Okay, now this next one right here, it says if the energy of a wave is 9.00 times 10 to the negative 19th joules, find the frequency and the wavelength. Okay, the thing that I've given you here is joules. Joules. Joules is energy. So this is an E. I will need to choose an equation that has an E in it, right? They want me to first find the frequency and then find the wavelength, right? So you're like, okay. Well, E is only in one of my equations. Sorry, I didn't label my wavelength. So they want you to do these things. And they actually didn't really specify which one they want you to do first or second. But if I go look at my equations and I find E, he's only in an equation with frequency. So maybe I solve for frequency first. And then if I have frequency, I can use that to solve for wavelength. Okay, so let's do that. That's a good strategy. So I'm going to first solve for frequency using the energy equation. And once again, guys, my energy equation is this guy. I got to get frequency by himself, right? So frequency by himself, I got to get rid of his little H buddy that is sitting next to him. Those go away. And then I have frequency is equal to energy over Planck's constant. Yes, you see how we did that? And then I just grab my values and I go, cool. Sorry, my brain started to fall apart there for a second. 9.00 times 10 to the negative 19th joules, right? And then my Planck's constant is, oh, it looks like an N. It is an H. Sorry about that. It is 6.626 times 10 to the negative 34th joules seconds. I grab my calculator. I am ready to go. This is going to be fun. We got some E buttons going on with us today. We got 9.00. We got E. Oh, y'all can't see. I feel like I'm so bad at that. Okay. To the negative 19th. Divided by 6.626 E negative 34, right? And then I get this. So I'm going to write this down, but I'm not going to get that out of my calculator because I don't want to round that too short. I want to keep that unrounded version in my calculator because I know I'm going to use that to solve for wavelength here in a second. But I can write down my answer for frequency here on my paper and use it in the correct number of sig figs for me to correct or grade, and then you guys can move on to solve for the other one. So I have 1.36 times 10 to the 15th, and the units for frequency are hertz. Once again, the number of sig figs was 3 going in. So the number of sig figs that I've expressed for my frequency is also 3. So now I got a frequency. If you want, you can now label this V. I can use that frequency to solve for wavelength using my speed of light equation. So you can either use your triangle and cover up wavelength, right? Or you can know to get wavelength by himself, you divide both sides by V, and your wavelength is going to be equal to C over V. So plugging things in, I have 3.00 times 10 to the 8th meters per second, yes, over my frequency that I have right there, 1.36 times 10 to the 15th hertz, right? But hopefully in your calculator, you still have kept that unrounded frequency, because I'm going to take 3 times 10 to the 8th divided by that. And the way that you do that in your calculator, if you are not sure, you just go 3E8, and you can go divided by, and there is a second key function at the bottom of your calculator. Y'all's probably look way less old. There is an answer key. That means grabbing the answer from the top that you just solved for previously, which would be my unrounded frequency, right? So I'm going to go second and then hit that answer, okay? So it's now going to divide by that 1.35 whatever, right? Enter. All right, so that is my wavelength, right? I'm sorry, guys. Oh my gosh, all over the place, all over the place. Okay, so I got wavelength is equal to, and I need 3 sig figs because this is 3 sig figs, which came from my energy of 3 sig figs. So I've got 2.21 times 10 to the -7th meters, yeah? Now, honors kids, well, unbox it off, so you're like, Sabaka, I can see, this is great. Honors kids, you guys will be responsible for converting things from meters into nanometers. Also, you will be responsible for converting nanometers to meters if you need to plug it into one of these equations, okay? Now, we know that on the metric chart, a nano is 9 places away from my meter. So basically, a meter, I would have to multiply what I see here times 10 to the 9th. What that means for me is I've just got to add 9 to that guy. -7 plus 9 gives you a 2, right? So this expressed to nanometers, and you do not have to show work for this conversion. I do not need to see dimensional analysis because it is in essence moving the decimal, which if you want, you can take that out of scientific notation, look at it and move your decimal 9 places. I feel like that is a lot of mistakes for me. I just think about adding 9 to whatever that number is. If you were doing the opposite, meaning I gave you nanometers and you needed to take it to meters, you would subtract 9 from that, okay? So then, and I think I may make a different video lesson for us going over some of these problems on y'all's spectrum practice, because I really want to make sure our math is solid on this, because there's a lot of big old scientific numbers, and I will do that. I will do that for you. Look at me being so nice. Anyways, so I am adding an exponent of 9 to this exponent of 7. That's what happens when you multiply a 10 to a power. You are just adding those exponents by whatever you see. So I've got times 10 to the 2. Right, so I got 2.20 times 10 to the 2 nanometers. And here's something that's kind of cute and funny that is satisfying. Well, first of all, that is a correct answer. Like, we love that. But times 10 to the 2 means that decimal really is back behind here. Right? Which, if y'all will look at your electromagnetic spectrum, That's why we actually classify most wavelengths of light by nanometers, because it's actually a number that you don't have to write in scientific notation. So a 221 wavelength would be a little bit more energetic wave because it's a smaller wavelength, which means higher energy and frequency. So it's a little bit outside of our visible spectrum, more over here. And if we're representing that in terms of jumps, since it's a higher energy wave outside of our spectrum, we would expect a much higher fall than a purple color light. So that's something to keep in mind too with my electrons jumping through the energy levels. A lot of these transitions, a lot of them, considering my visible spectrum is so small, a lot of them we can't see because they're either too short or they're either too long, okay? So that's our lesson on this jumping through energy levels. That is what creates all light here on Earth, and I think that that is just the most exciting thing ever, and I'm like nerding out about this. But we will practice tackling a lot of these calculations together, and we'll be practicing knowing and being able to qualify what the properties of wavelength, frequency, and energy do as you represent two different things on the electromagnetic spectrum, comparing them to each other. So anyway, I hope you guys have a great day. That was so super fun, and I will see you guys later.